Okay, this is going to be the last video in this series, and it's hopefully going to be a short one because I'm just going to do this one question. It has two parts. It's a little bit longer of a question, but we'll go through it. So two versions of a standardized test are given, an April version and a May version. The statistics for the April version show a mean score of 480. So we have, I'm going to draw two bell curves. We've got for two different tests. The April version has a mean score of 480. And a standard deviation of 24. So if I go one standard deviation up, we're going to end up at 504. And I could keep going. I could go up to 2, could go up to 528. And I could keep going if I wanted to, but right now I'm just going to stop there. All right, and then the May version, the mean score is 510. And the standard deviation is 20. So one standard deviation above the mean would be 530. 2 above the mean would be 550. And again, I could keep going, but I'm not going to worry about it yet. And then obviously this was a phrase that kind of needed to be stated in order to start doing that. All right, part A. Joanne took the April version and scored in the interval of 510 to 540. So maybe I will go out at least one more standard deviation here. So we can go up another 24 here. And if I do that, that would bring me to 552. All right, so I'm going to change colors up and kind of highlight the region that represents Joanne, or Joanne's scores. All right, so Joanne scored between 510 and 540 in the April version. So I'm using, even though 510 shows up over here, I'm using the April version. So 510 is right around here. And 540 is right around here. And so the question asks the probability to the nearest 10,000th that a test paper selected at random from the April version scored in the same interval. All right, so we need essentially to do norm CDF for this. Okay, so we have norm CDF of from 510 to 540 with the data centered at 480 and a step size or standard deviation of 24. So again, I'm just going to go ahead and type that into the calculator. And if we go menu 652, lower bound is 510, upper bound is 540, mean or mu is 480, and standard deviation is 24. And we do that, we get 0.09944. So to the nearest 10,000th is 4 decimal places. So it says probability, we do not need to convert this to a percent. We just leave it like that. Okay, so the next part talks about Maria taking the May version, and it says, in what interval must Maria score to claim she scored as well as Joanne? So essentially we need to come up with an interval that matches over here the Z-scores, right? And so we have, let me actually fill in the graph better, right? So we had the Z-scores of +1, +2, and +3. And the z-scores at +1, +2, and +3 would have been 570. And we have to figure out the scores that correspond to the exact same position on this bell curve. So we essentially have to figure out what the z-scores are for 510 and the April version. We can use the z-score formula, or we could use kind of a little bit of reasoning here. One thing we could actually take advantage of is 540 here, right? 540 falls perfectly in the middle of 2 and 3, right? This is a z-score of 2.5 because it's 12 points above this z-score, right? 28, 528 plus 12 is that, and then plus another 12 will bring me to there, right? So it's a z-score of 2.5. For that matter, I could actually kind of think about this the same way, right? This is 6 points above 504, and then plus 6 would bring me to 516, plus another 6 would bring me to 522, plus another 6 brings me to 528. So this is a quarter of the way. So 1 1/4 for the z-score there. So now I've just got to figure out what would the equivalent z-score be here, or the equivalent score of the z-score of 1.25, right? So z is 1.25 and z is 2.5. Well, 2.5 should be easy, right? Because what's halfway between 550 and 570? Well, that's just 560. And 1.25 still shouldn't be too bad, right? It's 1 1/4. So a quarter of the way between 530 and 550 would be 535. And so those are the two scores that we should expect to work. Now, just to make sure, I'll show you the formula, right? So we have the z-score formula. We'll do it that way. We have z equals data point minus mean over standard deviation. So we are looking at the z-score for 510 minus 480 over 24, and the z-score for 540 minus 480 over 24. And when I calculate these, we get 30/24, which is 1.25. And for this one, we get 60/24, which is 2.5. And so now we could go back to the formula again and say, well, now I know the z-scores. So I could say 1.25 equals new data point minus new mean over new standard deviation. New, or z-score of 2.5 equals new data point. So maybe I'll label these as x1 and x2 over minus 510 over 20. And I could solve these for x1 and x2 if I wanted to, right? So if I multiply 20 by 1.25 here, we would get 25 equals the data point minus 510. And add the 510 over, we get 535. Also, I could do 2.5, right? When I multiply, maybe I'll show the here. Right, I'm multiplying by 20 here to cancel out the 20 there. I'm multiplying by 20 here to cancel out the 20 there. And so when I do 20 times 2.5, we get 50. And so that's the other data point, minus 510. And so if we add 510 over, we get 560 as our other data point. And so my range of values here is going to be some 535 to 560. My last check is to use norm CDF on the calculator. Right, if I do norm CDF with the new information, I should get the same exact percent. All right, so if I go menu, 652, lower bound, we are making the assumption it's 535 up to 560. The new mean on the May version is 510. Standard deviation is 20. And we do that calculation and we get the same exact probability. So this is the answer. All right.